In this video, we're going to talk about similarity transformations, and listed here are several transformations, the first three of which are what we call rigid. For example, if we take this figure right here and we translate it, kind of move it like we would a salt shaker to the right and then up, the images would be superimposed on one another and they would be congruent. Same thing if we rotated a figure. So if we took this figure and rotated it, kept it the same side, and then translated it, same thing. We would get a congruent figure. Reflection, also a rigid transformation. So all three of these result in a congruent image. However, the fourth and final transformation listed is a dilation. And with a dilation, you have both a scale factor and a center of dilation. So if we were to take this and resize it, the pre and post image would not be congruent, but they would be similar. Therefore, one definition of similarity is if we can take a pre-image and we have a post image, could be a different size, different orientation, but eventually by rotating it, translating it, reflecting it, and then dilating it or shrinking it, we can superimpose the image. So that is one definition of two figures that are similar. It is very important to note, folks, that there's different criteria to determine if two triangular figures are similar versus a quadrilateral. So for example, when you have a quadrilateral, the criteria are more strict. And here's what I mean by that. Okay, if you have a square and a rectangle, both of these figures feature all angles at 90 degrees. However, these figures are not similar. With a triangle, all it takes to be similar is to have two angles that are congruent, the so-called angle-angle theorem. These will automatically be similar. And of course, if two of their angles are congruent, then the third angle has to be congruent because all the angles in a triangle add up to 180. But look, these are not similar, and here's why. When you're dealing with a quadrilateral or other polygons that have 4 or more sides, in addition to having all the angles the same, all the sides have to be proportional. So what do I mean by that? Suppose this square has a side of 4, and by definition, a square is going to have all sides equal. And for the rectangle, we have the length as 8, and the width remains at 4. To get from the pre-image to the post-image, there's a scale factor involved. In other words, we have the original length times a scale factor, in this case that would be 2, gives us the corresponding final length. But look at this scale factor. If you go from this side to the corresponding side on the rectangle, our scale factor would equal 1. That means these two figures are not similar. In order for them to be similar, that scale factor has to be consistent for all of the post-image sides. The formula I like to use for a scale factor, I find it's very helpful, is that the new over the original length is equal to the scale factor. And remember, the way I remember this is the New Orleans Saints playing the San Francisco 49ers. And if you multiply both sides, you'd get new equals the scale factor times the original. And that's what we did up here in this figure. Okay, here's our new, which is the 8, and that is the original times the scale factor. And here it is. The new equals the original times the scale factor. So one more time, even though these two images have all angles the same, these are not similar. In order to have similar quadrilaterals or even higher level polygons, you have to have the same scale factor that brings the pre-image to the post-image, and that scale factor has to apply for all of the corresponding sides. This similarity transformation that maps the larger trapezoid to the smaller trapezoid. So the first thing we notice, the fact that I use the words larger and smaller, it means we're going to have a dilation. And in this case, we're going to have a shrink. So the first thing I'll do is pick a segment that's easy to evaluate. For example, we're not going to use the length of that segment, but rather we're going to use either the length of this horizontal segment or the vertical segment, where we can easily count the number of boxes. So here we could see that the original length of this segment PQ, which corresponds here to XW, has been reduced by 1/3. So I know that there's been a dilation with a scale factor of 1/3. Remember, the scale factor is the number that's multiplied. You take the original length, you multiply it by the scale factor, and you get the final length. So in this case, the scale factor is going to be 1/3. So what I'm going to do here is I'm going to pick one point, and I'm going to look at the coordinates, and then I'm going to scale them down by 1/3. So let's look at Q. Q starts out as -3, 3. So what I'm going to do is shrink them down by multiplying by 1/3. So that's going to give us -1, 1 for Q prime. Now, the final point on the final image here, I wish they would have labeled this as Q double prime, P double prime, etc. But this is the final point that's going to correspond to the original point, which was Q. So if this is Q prime here, and this is effectively Q double prime, then it's clear that there was a reflection over the y-axis. So the transformations that were performed here was, number one, a dilation with a scale factor equal 1/3, and secondly was a reflection over the y-axis. You could see it here as well. Here, the solution showed reflecting over the y-axis first and then shrinking. So this is not a translation, obviously, because as you move from red to green, which is the final, clearly there is a dilation in the form of a shrinkage. Again, the word dilation is similar to when we use rise over run in graphing lines. So as we all know, the rise could actually be in the negative direction. Well, the word dilation could also apply to a shrinkage. In this next video, we are mapping the larger parallelogram that's located in this area to the smaller parallelogram. So this would be your A double prime here. Now, clearly we have a dilation in the form of a shrinkage. We also might have a translation. So I always like to do the translation last because it's the easiest to do. So let's first consider the fact that this is a translation. Okay, they didn't do us any favors here because they have these points. Actually, no, I take it back. See this line here, GH has 2 boxes, whereas originally it had 4 boxes. So clearly, as we went from a length of 4 to a length of 2 with the corresponding side, it was multiplied by the scale factor equal to 1/2. So I'm going to take the original A coordinates, and in order to find A prime, which is the intermediate figure, I'm going to just multiply the x and y coordinates by the scale factor, which in this case is 1/2. So our original x coordinate is +1. So our new x coordinate is going to be 0.5. Okay, kind of a nuisance. And our original a coordinate, I'm sorry, the original y coordinate for point A is +6. We're going to multiply that and say that that is now +3. Okay, so our A prime point, which is temporary, is going to be 0.5, 3 right here. That's going to give us a smaller image that would now match the size of our final image. Now the question is, how did we translate from point A prime down to a double prime? So now our first step, therefore, was a dilation. Scale factor equals 1/2. And then our second is a translation. And it appears to me that the x coordinate went from 0.5 to 2.5. So the dilation there would be the translation would be x plus 2. And it looks like the y coordinate went from 3 down to 0. So it would be y minus 3. So these would be your two transformations. One is a dilation, one is a translation that leads to a similar figure. Not congruent, but similar. In this next example, we're asked to list the similar transformations that result in this white image being mapped to the blue image. Now notice the final image is a double prime. That means there should be two transformations. I say that because it looks to me like you could, if you use C as a center of rotation and you draw a line to B, for example, and rotate that line 90 degrees clockwise, that would put you at B double prime. But they want us to have an intermediate transformation. There's still going to be a 90-degree clockwise rotation. And how do I know that? Look at this original direction that the point at point A is pointing to. It's pointing to the left. And in the final image, if you extend that point upwards, that is going to be pointing upwards. So how do you get from a line that's pointing to the left to a line that's pointing up? That's a 90-degree rotation in the clockwise direction. So we know that's going to be part of this transformation. And I like to do rotations, reflections, or dilations before I do any translations. Translations is the easiest. We do that last. So the other thing about this problem I didn't mention is any rotations have to be about the origin. So let's go ahead and rotate this white figure 90 degrees about the origin. I've done an entire separate video on this type of problem, but in essence, if you take the original A coordinates, which are 0, 2, in order to get A prime after a 90-degree rotation, these have to be switched, and then you pick the sign that accommodates the location with respect to what quadrant it's in. So here we would, in our minds, draw a line from the center of rotation, which is the origin, to the point in question. This is going to be A prime, an intermediate point, and we take that line from the center of rotation to the point that we're rotating, and then we rotate 90 degrees clockwise, and you could see it's going to put that A right on the x-axis. So the new coordinate points are going to be 2, 0 for A prime. Okay, let's now do B prime. So B starts out with the coordinates 3, 4. Since it's a 90-degree rotation, we are going to swap the integers. We're not going to look at the sign yet until we figure out what quadrant we're going to be in. Now, if you draw an imaginary line from the point that we're rotating to the center of origin, that would be our imaginary line. And we envision rotating that 90 degrees, we are going to be in the fourth quadrant. And in the fourth quadrant, the x-coordinate has to be positive and the y-coordinate has to be negative. So our b prime is going to be positive 4, negative 3. Okay, now finally our c prime, we're going to look at our c value. Our c value starts out with the coordinates. Let's do that over here. C starts out with the coordinates 3, 0. To get c prime, we're going to flip the integers. So it's going to be 0 and then 3. And then we're going to envision drawing a line from the center of rotation to the point in question, which is C. And we're going to rotate 90 degrees, and that's going to bring us to the y-axis. So the coordinates on the y-axis would be 0 and negative 3. So here is going to be our C prime. So let's clean this up just a little bit. We don't need this anymore, nor this. And let's look at our intermediate triangle, which again only has one prime listed. Okay, so that's a 90-degree rotation about the origin of that white figure. Now we ask ourselves, okay, how do we get from B prime to B double prime? And we could see that this involved a translation 3 units in the x direction, in the positive x direction, and 3 units in the y direction. So this transformation sequence is going to be number 1, a rotation of 90 degrees clockwise about the origin, and secondly, it's going to be a translation where we add 3 to both the x and y coordinate. In this next problem, we're asked to determine if these two figures are similar. So the mistake here is to notice that this has 4 right angles and this has 4 right angles, therefore they have to be similar. And it is not true. In a triangle, if 2 of the angles are congruent, then the angles are similar. However, in other polygons, quadrilateral being an example, in addition to all the angles being congruent, you have to have proportional sides. So let's look at the corresponding sides, and we see that this quadrilateral starts with the letters PQ and the image starts with the letters WX. So let's look at those two sides, P to Q and W to X, because they are indeed corresponding. So you see here that this is a length of 2 and this is a length of 4. Therefore, to get from the original, if you multiply by the scale factor, to get the final, that scale factor has to be 2. Now let's look at another corresponding side. We see that Q to R corresponds with X to Y. So we look at Q to R, that line segment is 4 boxes long. So if we multiply by a scale factor times 2, we expect this to be 8, if indeed these figures are similar. However, if you count the boxes, you see that this is only 7. So these are not similar because the scale factor that takes this side to its corresponding side in the image is not the same that takes this side to its corresponding image. These are not similar. Here we are asked to determine if triangles RST and XYZ are similar. One of the criteria for being similar is if you can take an original polygon and map it to an image using a series of transformations. Here, if RST is the original image and XYZ is the final image, clearly there's been a dilation and clearly the scale factor has to be greater than 1. So we look for the corresponding sides, and we're going to say that ST is going to correspond to ZY. The original has a length of 2, and the final image has a length of 6. Therefore, we say to ourselves, if this is the original 2 times what scale factor would give us 6, that would be a scale factor of 3. So we need to test these points, which are conveniently given to us, pre-image and image. And we find if we multiply all these x coordinates by 3, we get the image points. Let's look at S. 1 times 3 gives us 3. Negative 1 times 3 gives us negative 3. Therefore, these images can be mapped onto one another using a scale factor of positive 3, a dilation. In this next problem, we're told that Bill created a sequence of transformations that moves this trapezoid on the right to this on the left. And they actually give us the transformations themselves, and they ask us to place them in order. So the first thing I notice here is I'm going to pick a point. So let's pick this point right here and call that A. And we're going to pick the point where this angled line joins the short horizontal segment. So here's the angled line joining the short horizontal segment. So that's going to be point A triple prime. Okay, so let's look at what they give us here. They talk about reflecting across the x-axis, translating 6 units down, and rotating 90 degrees clockwise about the origin. Now, the final position is way up here in the second quadrant, so there's no way that translating 6 units down is going to be the last transformation. So this is either going to be first or second. So let's do it first and see where that takes us. We can always go back and do it second. If we're going to translate 6 units down, and again, all we need to do is focus on one point. We can ignore the rest of the trapezoid. So if I'm going to come 6 units down, we're currently at 4, 1. If we go 6 units down, we're going to be at 4, negative 5. That's going to be our A prime. So we can cross this one out. Our next choices are to reflect it across the x-axis. That would put us back up here. That's no good. So let's go ahead and try this, rotating it clockwise 90 degrees about the origin. So A prime is currently at 4, negative 5. So if we're going to go 90 degrees clockwise about the origin, in a previous video I discussed how to do that, and you're going to draw a diagonal from the point in question to the origin, and you're going to swing that line 90 degrees clockwise. And that's going to put us somewhere in this, the third quadrant. In my previous video, I talk about the fact that when you're doing a 90-degree rotation, or 270, which is a 90-degree rotation in disguise, you switch the integers, you don't even think about the sign yet. Then you go to the quadrant where you end up, and these integers have to assume the signage that corresponds with that quadrant. So in this case, they both have to be negative. So we now have our A double prime. It's going to be negative 5, negative 4. The only thing that's left now is to reflect it across the x-axis, and we see that A triple prime has the same x coordinate and the opposite y coordinate, which is what happens when you reflect over the x-axis, and that'll take us right to our destination. So our final sequence is going to be translate 6 units down, rotate 90 degrees clockwise, and then reflect across the x-axis. In this next problem, we're asked to identify the similarity transformations that take this red pre-image shown here, it's a trapezoid, to the black post-image, A double prime, B double prime, etc. The first thing I notice, of course, is that there's a size difference between the pre and post image. Therefore, we know we're dealing with a dilation. The second thing I notice is that if you look at the pre-image, the line segment AD is on the opposite side of the x-axis with the final image A double prime, D double prime. That suggests to me that there's going to be a reflection over the x-axis. Look here. You see that C and D, the line segment CD in the pre-image is on the same side of the y-axis as C double prime, D double prime. That means there has been no reflection over the y-axis. So let's go ahead and do that. If we look at this point A, initially at -2, -2, and we reflect that over the x-axis, recall that means keeping the x-coordinate the same and flipping the sign on the y-coordinate, we land at A prime as shown here. I went ahead and did the other 3 points, and I penciled in this trapezoid as the first image, or I should say the image from the first transformation. Next, we have to look at the dilation, and we can pick any of the line segments in the pre and post image for comparison, but this one jumps out at me. CD in the pre-image is 3 units long, and in the post image that is 6 units long. So therefore the scale factor is going to be 2. Recall, the original image times the scale factor gives you the final image. Now, if they had asked us as a part B to this question to determine if these two figures are indeed similar, what I would do is test the other pre and post segments just to make sure that they are proportional. So I would look at AD, which is this horizontal segment, and notice that it is 3 units long. I would apply my scale factor of 2 and then look at A double prime, D double prime, and I see that it is indeed 6 units. So 3 is the original length times the scale factor of 2 gives us the final length of 6 units. In this next example, we are asked to figure out what is the sequence of similarity transformations that take the white triangle to the red triangle. We can see that the vertices on the red triangle are listed as double prime, which means we're going to have 2 transformations. So the first thing I notice is if you look at segment AC in the original image versus A double prime, C double prime, it appears that it's been rotated clockwise 90 degrees. So let's go ahead and rotate this white triangle 90 degrees about the origin. If you look at point A and you draw a line from A to the origin and envision it getting rotated 90 degrees clockwise, it's going to end up in the second quadrant. So the original coordinates for A were -2, 2. When you do a 90-degree rotation, you switch the integers, which in this case it doesn't matter because they're the same, and then the new integers assume the signs of the quadrant. So here we're moving into quadrant 1. That means both of these are going to be positive, and that's going to be our A prime. So A prime is going to be right there. Okay. Next, what we're going to do is we're going to rotate point B 90 degrees clockwise. We're going to draw an imaginary line from B to the origin, and we're going to rotate that 90 degrees clockwise. That's going to bring us into the second quadrant. The fourth quadrant. So the original B coordinates are 2, 4. We're going to switch the integers, and we're going to get 4, 2. And then because we are in the fourth quadrant, the x value, x coordinate is going to be positive and the y coordinate is going to be negative. So our new point B prime is going to be 4, -2. Finally, we are going to rotate about the origin point C. If you take an imaginary line from the origin to point C and you rotate 90 degrees, you are again in the fourth quadrant. The initial coordinates of C are 2, 2, so we're still going to be at 2, 2, but we're going to be down here in the fourth quadrant, so it's going to be 2, comma, negative 2. So that is our new triangle after the first similarity transformation, which was a rotation of 90 degrees about the origin. So now we have this image as the penultimate image, and this is our final image, and you could clearly see that this is a reflection over the y-axis. So our sequence here, written in yellow, is going to be first a rotation of 90 degrees clockwise about the origin, and secondly is going to be reflection over the y-axis. In this next example, we are asked to figure out the similarity transformations that take this white figure to the red figure. And we notice from the vertices on the post image that there are 2 primes, which means there are 2 transformations involved. So the first thing we notice is the size discrepancy. We see that the pre-image has been enlarged. So we know there's a dilation with a scale factor greater than 1. The second thing we do is we look at the orientation of the figures to see if there's been any rotation and or reflection performed. So let's look at line segment BC. We see in the pre-image that it's horizontal, and we see the same thing in the post image. That tells me there's no rotations that have occurred. Secondly, let's review if there's any reflections. Looking at BC again, we see that B starts off on the left and C is on the right, and that same relationship holds true in the post image. That tells me there's been no reflection over the y-axis. Now let's look at the x-axis. We see here that B is superior or above to A in the pre-image, and that relationship indeed holds in the post-image. So there's been no reflection over the x-axis. So no rotations and no reflections. So what we're looking at, folks, is a dilation for sure, and then perhaps a translation. So let's do the dilation first, because we know that definitely occurred. So let's look at the length of the line segments. We see that BC starts off initially at 2 units, and if you look at the post image, B double prime, C double prime is 8 units. So we know that the scale factor of 4 has occurred during that dilation. So what I'll do now is I'm going to take a point, namely B, and I'm going to dilate it by a factor of 4, and I'm going to see what our B prime would be. So B is going to be, the coordinates of B are going to be 3, negative 2, and that's our original point. And to get B prime, we're going to multiply both of those by 4 and get 12 and negative 8. We also want to look at the final points, the B double prime, the final coordinates, I should say. So the final coordinates of B double prime are going to be negative 4, positive 4. Okay, so clearly the dilation alone did not yield the B double prime we're looking for. So the only thing left is a translation from B prime to get to B double prime. So we ask ourselves, how do we get from this x and y coordinates to our final x and y coordinates? We've already multiplied by 4, so far our translation looks like this: 4 times x and 4 times y. And if we look at how we got from positive 12 to negative 4, we clearly subtracted 16. And if we look at where we got from negative 8 to positive 4, we added 12. So we believe that this is our transformation. But let's check it with another point besides point B to see if we are accurate. Let's look at its neighbor, point C. So point C, starting out, is going to have the coordinates. Point C is going to be 2, 4, 5, negative 2. And C double, this is point C, that's our original. And C double prime, all the way down here in red, is going to be 4, comma 4. So let's see if this transformation of the original C takes us to the final C. So if we take the x value and we multiply by 4, we get 20, and we subtract 16, we get positive 4. And if we take the original y value, or y coordinate for point C, we have negative 2. If we multiply that by 4, we're going to get negative 8, and add 12, and we're going to get positive 4. So therefore, folks, this is our transformation, taking this smaller quadrilateral to the larger quadrilateral. In this next example, we're asked to figure out the similarity transformations that bring this larger trapezoid to the smaller trapezoid. Now here, they don't tell us how many primes there are in the post image, so we don't know if this is the result of one transformation or two or more transformations. So I hate when they do this. Instead of giving us prime or double prime in the original letters, they change the letters on us. So what I like to do in this situation is cross out these x, w, and z and use the original letters. Okay, so the first thing we want to do is look at the junction between the shorter of the two horizontal line segments and the slanted line. So the original point would be Q, and this would be Q. I'm going to call it double prime. That's a guess. I don't know if that should be single prime or triple prime, but I know that's the image of Q. So then what I do is I move horizontally along the short segment to get my P point post image. And then I'll come straight down to what used to be S. So coming straight down, this is going to be S double prime. And finally, I'm going to move horizontally along the longer horizontal line segment to get to R. And we do that, and this is going to be R double prime. Okay, so now having done that, I take a look at what's going on. We know now this is the post image, this is the pre-image, it's bigger. So we know there's going to be a dilation with a scale factor that's less than 1. Let's now look at the orientation of the figure. We see that the Q originally starts on the right side of the figure, but in the post image, it's on the left side of the figure. That tells me that there's been a flip or a reflection over the y-axis. So reflection y-axis. And now let's look at the up and down orientation. So we see in the pre-image that the P is superior or above the S. But in our post image, we also see that the P is above the S. That means, folks, there has not been any reflection over the x-axis. Finally, let's look to see if there was any rotations. The original line, PQ, is horizontal, and the final line connecting P and Q is horizontal. So that tells me no rotation. So the only thing that would be left is a translation. So we know that we have a dilation. That's right, what we know. We know we have a dilation with a scale factor that has yet to be determined, and there might be a translation to get us to this final value. I'm sorry. We know there's a dilation, and we know there's a reflection over the y-axis. My mistake. Okay, so the first thing we can do, we're going to pick a point that we're going to use to do this, and let's go ahead and pick point Q. All right, so the original coordinates of point Q are going to be -3, +3. -3, +3 for point Q. So let's go ahead and reflect that over the x-axis. I'm sorry, the y-axis, and figure out where that brings us. So if we start out at -3, plus 3, we know the y value is going to stay the same and the x value is going to be flipped. So we know, folks, that q single prime is going to be positive 3, positive 3. Okay, so that would put us over here for q prime. So clearly, q prime is not matching with q double prime. So now we're going to go ahead and do the dilation. Our dilation scale factor, if we look at the pre-image, we have a length of 3 for PQ, and for the post-image, we have a length of 1/3. So what I'm going to do is I'm going to now apply a scale factor of 1/3 to these two values, and we're going to be left with a q double prime of 1, 1. So if we check our final figure, we see that that matches. We could check the other points, but I assure you they will both work out. So let's review what we did. We figured out that there was a scale factor that was less than 1, and we confirmed that to be a scale factor equal to 1/3. That means the original times the scale factor gives us the final. So 3 times 1/3 gives us 1. Then we recognized there was a reflection over the y-axis. We actually did that first to get 3, 3, and we applied the scale factor to confirm the location of q double prime.